Hi there and welcome. We're going to be doing optimization problems today. This is section 2.5. I'm Rebecca Weaver, and let's get started with some examples. We're going to be maximizing area first. We need to find the dimensions of the rectangular garden of greatest area that can be fenced off on all four sides with 300 meters of fencing. All right, let's start with what we know. The garden is to be in the shape of a rectangle, so I'm going to draw a rectangle. The perimeter of it is to be 300 meters, so let's make a picture of the garden, labeling all the sides. All right, this is what I know so far, and since we know that the perimeter is 300 meters, we can now construct an equation based on the variables contained within the picture. We know that as we walk around this rectangle, x plus y is going to equal 2x plus 2y, and that's going to equal 300. This is called our constraint equation because these are the parameters that we have to deal with. We only have 300 meters of fencing. Now, the quantity we wish to maximize is area. Therefore, we need an equation that contains a variable representing area. All right, I know that x times y is equal to area, and this is going to be called our objective equation. Now, we're going to rewrite the objective equation in terms of a, the variable we wish to optimize, and either x or y. We want to kind of minimize variables here. So we're going to do this using the constraint equation. Since it doesn't make any difference which one we select, we just choose x, but you could choose y. So we have 2x plus 2y equals 300. This is our constraint. So when I solve this for y, I get y equals 150 minus x. Next, what I'm going to do is substitute this in for y in our objective equation so that the objective equation is only going to have one independent variable. So the area equals x times y. We're just going to plop 150 minus x in for y. We're going to distribute, and then we're going to graph it. We have that the area equals 150x minus x squared. I would like the maximum area, and I can see that maximum area occurs at the vertex of our parabola. So the maximum area is going to occur somewhere right in here. Looks like, all right, exactly dab smack in the middle. So I'd say it's right there at 75. Let's make sure, since the graph of the function is obviously a parabola, then the maximum value of a along the vertical axis would be found at the only value of x for which the derivative is equal to 0. So it's that top part, that vertex, which is what we said. So we have our area function. We're going to take the derivative. We're going to set it equal to 0, and then we're going to solve for x. And what did we get? 75. Therefore, the slope of the function equals 0 when x is 75. Therefore, that is the x value for where the function is maximized. Now we can use this constraint equation to determine y. If I know that 2x plus 2y equals 300 and x is 75, well, that means that y must be 75 as well. The dimensions of the garden will be 75 meters by 75 meters. Now, if a rectangular garden of area 75 square feet is to be surrounded on 3 sides by a brick wall costing $10 per foot and on one side by a fence costing $5 per foot, find the dimensions of the garden such that the cost of materials is minimized. Ooh, this is a little different. Below is picture the garden. The red side is going to be the side that's fenced, and the quantity that we'll be minimizing is cost. Therefore, our objective equation will contain a variable representing cost, C. So now we're going to plug these values in. Cost equals the quantity 2x plus y times 10 plus, which is what the cost for that side was, plus y times 5. This cost equation then becomes 20x plus 15y. This is now our objective equation. We're going to determine the constraint equation. The only piece of information we've not used yet in some way is that the area is 75 square feet. Now, using this, we're going to create a constraint equation as follows. 75 equals x times y. We're going to rewrite it so that we can isolate one of the variables in it, and we're going to just choose x is equal to 75 over y. We're going to rewrite the objective equation using the substitution that we just acquired from the constraint equation. And we're going to get, we have our cost equation, which is 20x plus 15y. And replacing x with 75 over y and simplifying, we're going to get that cost is 1500 over y plus 15y. We're going to sketch the graph of this function, and we get something that looks like this. So we need to minimize our cost so I can see about where that's going to be, and it appears from the graph that there's exactly one relative extremum, a relative minimum around x equals 10 or x equals 15, somewhere in there. To know exactly where this relative minimum is, we're going to set the first derivative equal to 0 and solve, since at this point the function will have a slope of 0. So here's our cost equation. Take the derivative. We're going to get that c prime is negative 1500 over y squared plus 15. We're going to set this equal to 0, and then we're going to solve for y. When we do that, we end up with y equal to positive negative 10. Of course, I'm not going to have a negative 10, so I would say that it equals positive 10 because I can't have a side that equals negative 10 in length. That wouldn't make sense. Therefore, we know that the cost will be minimized when y is 10. Now, we're going to use a constraint equation to determine the corresponding value for x. We just plug that y equal 10 into our 75 equals xy, solve for x, and we get that x is 7.5. This means that the dimensions that will minimize cost are x equals 7.5 feet and y equals 10 feet. Pretty nifty. Let's look at another example. We're going to look at an example where we're looking at volume. A canvas wind shelter for the beach has a back, two square sides, that's important, and a top. Find the dimensions for which the volume will be 250 cubic feet, and that requires the least possible amount of canvas. Here's a picture of our wind shelter. Okay, all right. I see my square side there. That was important. The quantity that we'll be maximizing is surface area. Therefore, our objective equation will contain a variable representing surface area. So I need to compute the area of each of those sides and see what I get. So here we are. We have our area. We have x times x plus x times x plus x times y and plus x times y. This is going to simplify to the area is 2x squared plus 2xy. Now this is our objective equation. Now we're going to determine the constraint equation. The only piece of information we've not yet used in some way is that the volume is 250 feet cubed. Using this, we create a constraint equation as follows. 250 equals x squared times y. This is our constraint equation. We're going to rewrite the constraint equation, isolating one of the variables once again so that we only have either just an x or a y. The easiest one to do here would be to make it read y equals, so that's what I'm going to do. So I have y equals 250 over x squared. Now we're going to rewrite the objective equation using the substitution that we just acquired from the constraint equation. And so we're going to write our objective equation down, substitute in for y, and we're going to simplify, and we get that the area equals 2x squared plus 500 over x. We can use this to sketch a graph of the function. When we do this, we see that we have one relative extremum. We have a relative minimum somewhere around here, around 5. Don't even know exactly where it is, but we'll figure that out in just a second. So it appears from the graph that there's exactly one relative extremum, a relative minimum around x equals 5. We looked at that, said that too. To know exactly where this relative minimum is, we need to set the first derivative equal to 0 and solve, since at this point the function will have a slope of 0. So here's our area equation. We're going to take the derivative, and when we take the derivative, we find that a prime is 4x minus 500 over x squared. Set this equal to 0, And then we're going to solve for x. What we will end up with is that x equals 5. Therefore, we know that the surface area will be minimized when x equals 5. Right there exactly on the nose. Now we will use the constraint equation to determine the corresponding value of y. So we write down our constraint equation, plop in a 5 for x, and we find that y equals 10. So the dimensions that will minimize surface area are x equals 5 foot and y equals 10 foot. Now, if we want to do some optimization problems, we have a few suggestions. The first thing, my favorite thing to do is draw a picture, if possible. I really can't do any of these problems without drawing a picture. I always do it. Next, I need to decide what quantity, Q, is to be maximized or minimized. I know I'm going to have two different equations. I'm going to have an objective and I'm going to have a constraint equation. So I decide, write down both of those two functions, assign letters to the other quantities that may vary, determine the objective equation that expresses Q as a function of the variables assigned in step 3, find the constraint equation that relates the variables to each other and to any constants that are given in the problem. Use the constraint equation to simplify the objective equation in such a way that Q becomes a function of one variable. We do that every time, and that's what you'll need to do. Determine the domain of this function. That just means make sure that we don't have negative distances and so forth that we were looking at before. Sketch the graph of the function obtained in step 6 and use this graph to solve the optimization problem. Alternatively, you can always use the second derivative test. All right, well, that concludes this section. And if you have any questions, be sure and email me. And have a wonderful day.